So the next talk is by Blais, who's going to tell us about VC dimension and sample-based testing.
Thanks, in India. The work I'll be talking about is joint work with Renato Ferreira Pinto Jr. and Nathan Harms. And I just want to mention Nathan Harms will be participating this week. I think he might even be here right now on Zoom. So he'll be here and happy to answer any questions you have. I'll also be happy to answer any questions I have, but you may have. But let's first talk about our topic. I want to talk about kind of one of the most basic questions that's driven a lot of research in property testing, which is just this very simple or general question: which classes of functions can we test more efficiently than we can learn? And ideally much more efficiently, asymptotically, or maybe polynomial factors better. To make this question precise, you need to specify exactly which setting you work in. And I want to ask maybe what should be the most fundamental setting to study this in, at least from the point of view of learning. What if we actually ask this question in the model that corresponds to just the PAC learning model, the original PAC learning model? And here there's something a little bit surprising to me anyways, which is that despite all our research on this general question, for this specific model, we really have very, very few results. At the very least, before I started this project with Renato and Nathan, if you told me about any of the classes that we typically study in property testing or in learning, I would not have been able to tell you if we could actually test it more efficiently than we can learn the same class or not, for essentially any class that we could think of. So let me actually make this question precise and introduce some of the notations, definitions we'll use. The PAC learning model, I'm going to, just for simplicity, talk about the proper learning framework. And here there's two things that are important. There's a distribution D, which is on the domain of some unknown function f. And you get samples x1, x2, all the way to xm from this distribution. And for each of those samples, you actually also get to see the label, the value of f on this input. And you don't know f, all you know is that it comes from some class h of functions. And what you want to do is output a function that's close to f. So distance at most epsilon from it, where here the key point is that this distance is measured according to the unknown distribution D. Now, what we're going to say is that mlearn of h is the minimum number of samples required to learn a function from this class. And this is kind of how we'll be comparing testing and learning in terms of sample complexity. So this is the learning task. And now if we want to compare apples to apples for the testing task, we want the model to be kind of the same, where again, I get x1 through xm drawn from some unknown distribution D. But now I'm not promised that the function f actually comes from the class h. Indeed, my task is to distinguish the case where f comes from this class from the case where f is actually far from every function in the class h. And now I, again, want to ask how many samples do I need to do this? I'm going to write this as mtest of h. So what do we want to ask now? We want to ask how, or for which classes can mtest of h be much less than mlearn of h? I guess implicitly I'm making this assumption here that learning has to be at least as hard as testing. This is a classic result of Goldreich, Goldwasser, and Rahn, and it carries over to many different settings for testing and learning. It carries over to this setting as well. So even in the standard PAC learning model or the distribution-free sample-based testing model, the algorithm, the testing by learning algorithm does apply. And so it means that if we ignore the additive 1 over epsilon term here, the sample complexity for learning can never be smaller than the testing complexity, the samples that I need to test the same class. And also, actually, even already in the same paper, there was an example shown that there are classes where this inequality can be very large. There can be a huge gap between testing and learning sample complexities. And here, this example, it's good to keep in mind because it might show up again later in this talk. Just take the class H of all the functions that are completely unrestricted if the first bit is 0, but always take the value 1 if the first bit equals 1. And so here we can easily convince ourselves it's very hard to learn these functions, but it's actually very easy to test them, even in this case when we only get samples. And even if it's under an unknown distribution, if it's far from being in the class, it won't take many samples before we actually get evidence that the function is not in the class. So we can test it with a very small number of samples. Okay, but now, as I mentioned, if you actually ask me about other natural classes of functions, I didn't know until very recently of any examples that I could give you that are natural where there is a big gap between testing and learning. In our work that's on the archive right now, you can see that actually there are two very basic classes where we can show a large separation, a quadratic separation between the two juntas and monotone functions. But actually, what I really want to talk about today is the other direction. It turns out there are many other classes that are natural for which you can't actually hope for this kind of separation. So specifically, there are many natural classes of functions like half spaces or intersections of half spaces, PTFs, decision trees of small sizes, and quite a few other ones, where the separation between the two is going to be at most a log factor. This is the lower bound I actually want to talk about. And what I actually want to talk about to kind of give you an idea of the proof and the main idea that I want to introduce about this, I'll be talking about half spaces. So before I rush through with the proof of half spaces, this is a good point to ask if there's any questions in general.
So in all these classes, is the learning complexity something which is, I guess, dependent on the ambient dimension, right? So the testing, I guess I just wanted to say, ask, like, is the log factor hiding just a factor dependent on epsilon, or is it more than that?
It's going to be a log factor in the learning sample complexity itself. So not just
Okay.
in epsilon, but in the learning sample complexity.
Okay.
We'll actually see it. It turns out this log factor will be familiar, especially given the talk that we just saw about distribution testing. Okay, let me explain this a little bit better, what I mean by this answer. So here, just to have some notation, I'll write LTF for the class of half space functions when you're in n dimensions. So r to the n, I think all the results with a slightly different argument, they all hold if you're looking at Boolean functions as well. So half spaces over the Boolean hypercube, all the results will carry on over. We just need to change the proof a little bit. But okay, so what do I want to prove? I want to prove that the testing, the number of samples I need to test is roughly the same as the number of samples I need to learn half spaces. How do we do this? Well, the first part is easy. If we're only asking about sample complexity for learning, and I'm not worried about runtime, which I'm not for this talk, then actually it's only a question of computing the VC dimension of the set of half spaces. So half of this theorem of determining the number of samples I need to learn half spaces is kind of this classic, well-known, well-understood task in learning theory. So we're left with the other half of the task. We need to determine the number of samples we need to actually test this same class. And the real main message I want to get across today is actually, it turns out there's something very similar to VC dimension that we can use to also compute this sample complexity. So not only the learning sample complexity, but also the testing sample complexity can be determined using VC-like dimensions. So, okay, so VC dimension, the standard definition here, just to introduce again, the notation I'll be using. H, I'll use to represent my class of functions or the property I'm testing. The domain will always be represented by X here, and I'm only looking at Boolean functions. And now the key concept here, the key combinatorial concept is shattering, where we say a set of points from the domain X is shattered by H if there is a function in H that takes all possible sets of labels on those points. And the VC dimension is just the maximum size of any set that can be shattered by H. And now this fundamental theorem of learning says that once you know the VC dimension, you also know the learning sample complexity, at least in the setting where I'm thinking of it, where I think of epsilon as a constant, then it really completely determines the number of samples that you will need. Okay, so now I'm promising you that we can do something similar with testing. And what I want to do is actually take two slight variants of VC dimension. The first one is to say, instead of just looking at all possible sets to compute the VC dimension of H, I can do the same thing restricting my search to any subset of the domain. So for any subset S of X, I can say the VC dimension of H with respect to S is defined exactly as before. It's just the size of the maximum set that can be shattered by H, just under this restriction that I'm only looking at subsets of S. And so this has been defined before, but usually if you care about learning, you won't really look at this notion because you can only increase by taking S to be the entire set X. And so that's most often what's being done. But for us, it's actually going to matter that we like looking at VC dimension with respect to a subset of the domain. And once we have this, I only want one more definition, which I don't think has a name in the literature. So we're going to call it lower VC dimension, just because it always takes a lower value. It's bounded above by the VC dimension. And what I want to do is I want to take the exact same definition of VC dimension, but I want to replace the there exists symbol with for all. So what does this mean? I'm going to say the LVC dimension with respect to a set. It's just the maximum cardinality K, where every set of size K, or at most K, is shattered by H. So instead of just asking for the maximum size of a set that's shattered, I want to say the maximum cardinality I can get that guarantees that all the sets are shattered by H. So this is VC dimension, and this is LVC dimension. And I just want to mention a few basic observations about those two measures, essentially as an excuse to give you a bit of time to ask more questions about this if anything is not clear. But what can we say? I just mentioned LVC is always bounded above by VC for any subset, and this is just by definition itself. But we also know that the two dimensions really are different from each other in the sense that this does not always have to be a very tight inequality. There are classes of functions for which the LVC dimension is much, much smaller than the VC dimension. And we can come back to the exact same example when we separated testing sample complexity to learning to see an example where actually LVC is constant, maybe 1, whereas the VC dimension is going to be extremely large, maybe as large as the size of the set, depending. So we do have examples where there's a large separation. We do know that one is bounded above by the other. And we also know that there's actually quite a few natural classes where the two are the same. So there are some cases where the two measures are very different, and there are other cases where the two measures are exactly the same. And in fact, for half spaces, this is the case. As long as you give me a set of points in general position, the VC dimension and the LVC dimensions will agree. And this is by the same argument that's actually used in standard textbooks for half spaces for just computing the VC dimension. The same argument actually gives you that the VC dimension is the same as the LVC dimension. Okay, but why does this help us? What I'm going to claim now is that actually just knowing that the VC dimension is the same as the LVC dimension for a large enough subset S is enough to give me a really strong lower bound on the testing sample complexity for half spaces. And specifically, I can state this lemma more generally to say for any class, if you have VC dimension being the same as LVC dimension, then the sample complexity will be up to log factor exactly this LVC dimension, which is here by this condition the same as the VC dimension. So all of those classes will have testing sample complexity at most a log factor better than the sample complexity for learning the same class. How do we actually prove this? The proof will fit in this one slide. The idea is going to be that we just pick a random function. And we're going to choose some distributions D over S. And we're going to be a little bit more careful how we pick our distributions. Now, the intuition being that if I pick a random function, it should be far from the class H. But this is actually not necessarily true. This will really depend on my choice of the distribution D. And if I look at this a little bit more carefully, I'll see that actually if D is a distribution that has a support of size much less than the lower VC dimension, then actually what this means is that it has to be consistent with some function in my class. So the function f, even though it was a random function, if you only look at it at a very small subset, it completely agrees with some function that's in the class. And on the other hand, if you do take D to have large support size, to have a lot of mass on much more than n points, then actually, yes, now our intuition is confirmed by the standard Sauer-Schelle or Sauer-Schelle peerless lemma that says, as long as I have many more points than my VC dimension, the probability that I happen to be close to some function in my class is going to be extremely small. So what does this mean? This means that actually, if I have a tester for H in this distribution-free sample-based model, I can estimate the support size of a distribution. And estimating the support size of a distribution is actually this very well-studied, nice problem in distribution testing where we know that you need n over log n samples. And so this actually is the sketch of the entire proof for why the moment you have LVC being the same as VC dimension, testing is at least essentially as hard as learning the class. Any questions about this so far? Okay, so now what I'm saying is we can put the pieces together and we get our lower bound between them by just using the VC dimension for learning, the main lemma for the lower bound, and we get our result. What's nice is we can apply this technique to many more classes. So there was, we saw that half spaces satisfied the condition that we needed for this lemma to apply. And it turns out there are many other classes where we have this condition that the VC dimension is equal to the LVC dimension. So this actually ties into some of the many structural properties of functions that have been studied in learning theory. So in particular, maximum classes always must satisfy this property. And there's another class of functions, analytic Dudley classes also must all be maximum, so they all satisfy this equality. So there's a few examples here of other properties that we can use or that we can prove lower bounds for using this same technique.
I think there's a question. So Joe asks whether n over log n is tight. Do we know if log n is the best number we can get here?
That is a fantastic question. That's going to be one of my last questions at the end. We don't know. And I'd be really interested to find out. I think it would be really nice if we could find out whether this log n is necessary. What I can say is it is necessary for this lemma. So the lemma itself, or the more general version of the lemma at least, we do know that the log n factor must be lost for some properties. So there is a tight upper bound in general, but I'll come back to this at the end. That's a really good question.
I have a more basic question. What's the maximum class?
I was hoping to skip over this to have everybody who's seen maximum classes just nod and say, okay, cool. The short version is this Sauer-Schelle lemma tells us how much the class can grow as you go over the VC dimension size for the samples. A maximum class is going to be a class where the inequality in this lemma is tight. So it's the one that grows exactly as the lemma satisfies, which to me always sounds like a very odd condition in the sense that it's not clear to me why this should give some really nice structural properties, but it does, which is why they've been studied quite a bit. I also want to raise one more question though, like what happens when you don't have this nice property? What happens if you're actually looking at a different class of function where you don't have the equality? And it turns out actually the real main lemma that we prove in the paper is much more general. It does apply, even when your lower VC dimension is not exactly equal to the VC dimension. And what we get then is the bound that's actually stated here in this lemma, so that the bound will be non-trivial, but only when the lower VC dimension is somewhat comparable to the VC dimension. In the extreme cases, then actually the lower bound is not meaningful. as you would expect, actually, because of the example that we saw where testing can be done with a query complexity that's really independent of the VC dimension. So I mentioned it can be applied for more properties this way. Just one more thing I wanted to just mention quickly. It actually, this kind of lemma applies for other problems that don't fit the general framework that I've been talking about so far of pack learning functions. It works for testing clusterability, and it works for testing LP feasibility in the sense that it was introduced by Epstein and Silwell earlier this year. And for clusterability, I can even state the result just a little bit more precisely here, let you look at it. Here we don't have a function, we just have a distribution of points, and we want to know if there's at most k centers where all the points are close to one of the centers, say unit distance at most from one of the centers. And so it's a nice result of Alon, Dar, Parnas, and Ron that you can test whether a distribution of points is k clusterable or whether it's far from k clusterable with a number of samples that's only roughly n times k, ignoring the log factor. And using our main lemma and the same kind of proof technique, we can actually show that this is essentially tied, again, up to these log factors. And that's it. Those are all the things I wanted to talk about. I just wanted to leave you with kind of 3 questions. What I skipped over this is how you actually prove lower bounds for the LVC dimensions for the classes where it's not equal to the VC dimension, or even showing that it's equal to the VC dimension. This is where there's a lot of specific arguments for different classes. But what's nice about this is that they're nice combinatorial arguments. So you can look at these classes of functions, have these combinatorial arguments that give you these results for testing sample complexity. So the obvious question is kind of to see for which other property this could hold, to see where else even LVC dimension could be used. But I wanted to kind of raise 3 other questions that are not this obvious follow-up question. And the first one is kind of related to the question that was asked before, like, is the log n factor necessary or not? I think that would be really interesting to understand when it's necessary and when it's not. If it's always necessary, if you always need, like if you have a matching upper bound of n over log n all the time, or if not. So if you do have a matching upper bound, for example, for half spaces, this shows us that actually testing is easier than learning by just the log n factor, but still, it would be easier. And on the other side, if you show that actually, no, we can improve the lower bound to order n, I think this would be equally nice because it would show that actually the support size estimation problem that's kind of hidden inside all these testing problems is not the only bottleneck. So it's a question of, is this the only bottleneck, or is there something else that could stop the query sample complexity from being lower? There's a second, again, I guess kind of obvious, but really interesting direction that we haven't had time to look at yet, so it's completely open, is what we kind of showed is that if you look at VC dimension, it can be used for giving you the sample complexity of testing problems as well, as long as you use some variance of VC dimension with it. And you could ask the same question about all these other notions of dimensions or complexities that have been used in learning. Do any of those dimensions also have analogs that work for understanding testing better? And the last question I want to leave you with is a much more restricted question. I don't think it has any deeper connections to the work that I've presented here today, but it was one of those annoyances that I'm hoping someone here in this workshop can resolve for me. What is the VC dimension of decision trees? As far as I know, the best known bounds are omega k, but order k log n for size k decision trees. And as far as I know, there has been no improvements on this in the last 20 plus years. But I'd be very happy to learn that I'm actually wrong here, that I just don't know about some results. That's it. Thank you very much.
Thank you, Eric. So we have a couple of more questions. So first is Arnab is asking, can you explain more on how you extend to functions on the hypercube?
Um, Everything I've said kind of applies as is until I get to the point, for example, here, where I'm talking about points in general position. We just need a slightly different argument to argue about VC and LVC dimension for half spaces. Here with the hypercube, I guess I forget exactly what we did for half spaces, but in all the cases, I kind of want to claim conceptually it's very similar for the hypercube as for the real space. So that's my half answer. Maybe my better answer is Nathan will be happy to tell you a lot more about it throughout this week.
So I've actually promoted Nathan. Nathan, you have panelists now, so you also wanted to add a comment, so maybe you can do that. Actually, did I do that successfully? Did I? Nathan, you can unmute yourself and.
Hello?
Yeah.
Hi, sorry. Yeah, I just wanted to revisit Joe Neiman's question from earlier about the upper bounds. So you asked if the log n is necessary, and so in general, yes, it's necessary because there's an order n over log n upper bound for testing symmetric properties, which matches it matches our lower bound.
Could I ask a question about the lemma? I think it was slide 13, the one with the sketch of the n over log n lower bound for the testing sample complexity.
Yeah.
I think I have a bad intuition here or something that like what about distributions? I mean, the same issues arise for estimating support size, but what if the distribution D is like has only a very, very tiny amount of mass on these
yes.
elements?
Yes, so here I am skipping over those details. You're right. So what we actually want to do, if I'm being a little bit more careful how I'm writing things, is we want to identify these distributions D that have mass at least 1 over n or proportional to 1 over n on each element in its support. And then we want to choose the support to be either fairly small or quite large. So there are additional structural properties that we need on D for this to actually be correct.
I see. Okay, that totally makes sense. Thanks, Eric.
Do we have any other questions? I mean, the next talk is 15 minutes from now, so plenty of time. Okay, so if not, then, well, thank you, Eric. And the next talk is by Rocco Savigio in 15 minutes. So do we like, okay, I guess we're not going to switch off the recording, but actually, do we just like take a break?